So welcome to Activity 4. This is kind of a continuation of Activity 3 because in the end I am going to be using the circuit to filter the output of the full-wave rectifier that we did in Activity 3. This is really cool. I have never before needed to do a full analysis and an analytic design of a rectifier because in all of my playing and hobbies, when I needed to filter a circuit, I just grabbed a capacitor, I grabbed a resistor, and tweaked them until they made sense. It was very, very trial and error. But of course, to make this video, I need to have a deeper understanding of what I'm doing so that I can impart onto you a deeper understanding of what you're doing. So let's jump in. So for this video, I'm going to be using Google Sheets, partly because anyone and everyone can use it for free. Now in the end, this is actually a very simple circuit and a very simple concept behind it. The way a low-pass filter works is you have a resistor and a capacitor in series with each other. If you remember back to voltage dividers, you have two resistances in series with each other. Resistors do not change their resistance based on frequency. So if you have an R1 in series with an R2, and you apply the input voltage across both, but then you measure only the voltage across R2, the voltage across R2 becomes your output. It is non-frequency dependent and it simply attenuates all frequencies equally. In this low-pass filter, the capacitor has a capacitive reactance which decreases with frequency. So at 0 Hertz, a capacitor is, for all intents and purposes, an infinitely large resistor, and you will see all the voltage across it. So at 0 Hertz, whatever the input signal is, that's what you're going to see as the output signal. As frequency increases, the capacitive reactance gets smaller, and so the voltage that you see across the capacitor gets smaller. What that gives you with the resistor in series with a capacitor is a frequency-dependent variable voltage divider, where you feed the input to the resistor and the capacitor together, and the output is just what you see across the capacitor. What we're driving towards with this is a low-pass filter with a 5 Hertz cutoff, meaning that at 5 Hertz, the attenuation of the signal will have an output that is 70.7% of whatever is fed into the input. And that 71% attenuation will just increase with frequency. So we have an input voltage. And although the full bridge rectifier output that we're going to be using has a peak voltage of 16 volts and an RMS voltage of 12, we're going to start off very, very simple with a 1 volt input. The next part is input frequency. When we get to the point of plotting this out, we're going to be putting the frequency on the horizontal axis, and it'll be logarithmic. So we're going to start off small, get big, and the increments that I use will look weird, but it'll make sense later. Since the formulas that we're using include things that divide by frequency, we can't actually use a frequency of 0 Hertz. So I'm starting off with a millihertz. Our circuit has a resistor, which to start off, I'm just going to use 1 ohm. It has a capacitor, and I'm going to start off with a 1 farad capacitor, just keeping all the numbers very simple to start. But guarantee we're not going to be using a 1 farad capacitor in your lab kit, considering I looked it up on DigiKey, and a 1 farad 16 volt capacitor is not only the size of a pop can, but it's also about $250 just for that one component. So you'll have to buy that yourself. I decided to add in the time constant, tau, for the resistor and capacitor combination that we have. It may not actually be used, but it is something interesting. So for a resistor that is 1 ohm and a capacitor that's 1 farad, the time constant which is the amount of time it would require for the voltage across the capacitor to rise from 0 volts to 0.632 volts, 63.2%, would be 1 second. The frequency-dependent reactance of our capacitor, Xc, is going to be equal to 1 over 2 times pi times frequency times the capacitance in farads equals 1 over 2 times pi times our frequency times our capacitor. Yes, I did. So at 1 millihertz, a 1 farad capacitor would behave similar to a 159 ohm resistor in series. Now, if we had 2 resistors in series, we could just simply add them together to see what the total impedance of this circuit was. But we can't do that because a capacitor or an inductor has a 90-degree phase angle that needs to be taken into account. So instead of simply adding R plus Xc, we have to add R, and we have to add C, but at a 90-degree angle. So we're really constructing a triangle where what we're interested in is Z, the hypotenuse of the triangle. So Z is going to be equal to the square root of the squares of the 2 components. Resistor value squared plus Xc, the capacitive reactance. At this point, I'm going to leave a gap because the gap is actually phase. And we're going to come back to that. You don't actually need phase yet. We can easily just look at what the output voltage would be on this row, because just like the voltage divider, where it's just 2 resistors, V out is going to be equal to V in times the fraction that the capacitor is of the total. Voltage in, 1 volt, times Xc over the total. Now obviously at this point, at 1 millihertz, the effect of this circuit is negligible. At such a low frequency, the capacitor is dropping almost 100% of the voltage, and the resistor is barely seeing any of it. So let's flesh this out and add a few data points. There are a few specific frequencies that we care about. We care about 5 Hz, which is the designed cutoff frequency. We care about 60 Hz, which is the input frequency. And we care about the output frequency, which is 120 Hz. I'm going to go beyond 120 Hz so that the chart is more interesting. And being that the frequency axis is going to be logarithmic, there's nothing stopping us from going quite a bit higher than that to be able to see what happens. So let's start off with a handful of frequencies that range from this essentially 0 Hz up to 10 kilohertz. And we're going to do this non-linearly. So we're starting off at a millihertz, and I'll go to 10 millihertz and 5 millihertz and 1/10 of a hertz, 2/10 of a hertz, half a hertz, 1 hertz, 2, 3, 4, 5, 6, 7, 8, just to get a bunch of data points around our 5 Hertz cutoff. 10, 20, 40, 60 Hertz, our input frequency. 100 Hertz, 120 Hertz, which is our output frequency, or at least our fundamental output frequency. And then 200, 400, 1,000, 2,000, 4,000, and 10 kilohertz. The input voltage is not going to change, so we'll just make that an absolute reference. And copy it down. And we'll highlight what we will be changing. Same with the resistor and capacitor values. These are not going to change from row to row, so absolute references. And highlight what will change. I'm not going to bother copying this down because it's not going to change, because the resistor and capacitor aren't going to change. It's just a point of interest. This, on the other hand, will change. So we'll drag it down. The total impedance is going to change, so we'll drag it down. The output voltage at each instance is going to change, obviously, so we're going to pull it down. And there's way too many decimals for me to care about, so we'll highlight those and reduce the number of decimal places to something reasonable, maybe one more. And finally, I'm just going to bold this. Now, I'm not going to bother with phase just yet, because we can get our first chart up that relates frequency to output voltage. Insert chart. And initially the chart looks empty, but that's because we're still on a linear scale. When you double click on the scale, you can go down and change it to a logarithmic scale, and we will see that very, very sharp cutoff going from 0 Hertz to almost 0 at 1 Hertz, and then relatively flat all the way up to 10 kilohertz. And the only other modification that I'm going to make right now is to change the vertical axis to have a few more tick marks. So grid lines and ticks. And the vertical axis and the step value is going to be 0.1. Close the editor and put the chart wherever you like. Now, as for phase is pretty straightforward. Phase is the relationship between R and XC, expressed as an angle, because the capacitor imparts a 90-degree phase shift. So the first way you can do phase is extremely straightforward. You can do the inverse tangent of R over XC. Bear in mind that Excel and other similar things, like Google Sheets, expresses angles in radians, not degrees. So, although this is the simple formula, and I'm forgetting at the moment the negative, in order to convert from radians to degrees, we divide by pi, and then multiply by 180 degrees. if we perform this out calculation, then it's going to be equal to E tan R over XC divided by pi times 180. And if we let that copy down, I forgot the minus. So at 0 Hertz, we have a 1 ohm resistance and a 1 farad capacitance with a reactive capacitance of 160 ohms. So the phase angle is about 0. As frequency increases, the resistor doesn't change, but the reactive capacitance drops to almost 0, and the phase angle changes accordingly. You also have a formula that you might be more familiar with in the case of this, which is the negative arctangent of 2 times pi times f times r times c, which will also need to be converted to degrees, divided by pi times 180. If we put that formula instead, equals negative arctangent 2 times pi times frequency times resistor value times capacitor divided by pi times 180, you will see no difference. Either formula works. And if we now plot this, frequency against phase, insert chart, and Google decided to do separate line charts, but that's okay. So if you just simply go down to use column B as labels, the labels are what become your x-axis. And just like with the output voltage, we need this to be on a logarithmic axis. So customize horizontal axis, logarithmic. And the title's rather messy, so let's just double click on that and change it to frequency versus phase. And the vertical axis, we're interested in where 45 degrees crosses, so let's change that to grid lines with a step of 15 degrees. And we'll force the minimum and maximum to actually be the whole numbers by going to the vertical axis, with a minimum of -90 and a maximum of 0. Close the editor, position it, and we'll just bump in the left side of this chart a bit so that the 0 Hertz lines up on each. Now, what are the values that we're interested in? The design for this is 5 Hertz. The input to the rectifier, although not so important, is 60 Hertz. And the output of the rectifier, which is important, is 120 Hertz, albeit a rather distorted waveform. We're looking for the phase to be minus 45 degrees or higher. So let's add some conditional formatting. So if the number is less than or equal to minus 45 degrees, sure, we'll stick with green. So now, at this point, it's very, very straightforward to play with these values and find what we need. What we need is to find a resistor and capacitor combination that results in minus 45 degrees phase shift, which will result in a 0.707 attenuation of the output versus the input, which is why I started off with the input as 1 volt, because when we see 0.707 at the output, we'll know that it'll be an additional confirmation that we are correct. So let's grab some arbitrary values. We're looking for this green to be at 5 Hertz or below. It is definitely below right now, and this would work wonderfully. And if we were to use a 1 ohm resistor and a 1 farad capacitor, then at 5 Hertz, our 1 volt input would be reduced to 32 millivolts, which is quite an attenuation. But we don't need to be so severe. Let's try 1,000 ohms with a 1 microfarad capacitor. So as we can see here on the chart, the minus 45 phase shift is happening above 100 Hertz. If we look at the green area where it's 45 degrees or higher, well, minus 45 or lower, but you know what I mean. That's at 200 Hertz. We can decrease the cutoff frequency by increasing the resistor or increasing the capacitor or increasing both. If we increase the capacitor by 10 times to 10,000, 10K, now our 3 decibel roll-off, our 3 decibel cutoff is at 20 Hertz. The same effect is achievable by using a 10 times bigger capacitor. So now we're at 10 microfarads. Just like a resistor, capacitors have fairly standard values. So we have, in this case, a 10 microfarad capacitor. What about a 100 microfarad capacitor? And now we've definitely achieved our result, but we've actually gone beyond where we need to be. So we can either use a smaller capacitor or a smaller resistor. The choice of changing the resistor or the capacitor is an important one because each has side effects. If you change the size of the capacitor, it has a very severe effect in the size of your device relative to changing the size of the resistor, which within certain limits doesn't physically change at all. Changing the resistor determines what your maximum current is. And since current times voltage is power, if you use a larger resistor, you decrease the power output of your circuit. So let's leave this at a 100 microfarad capacitor and instead change the resistor value from a 1K, which is a standard resistor, to a 470 ohm standard resistor. Pretty good. The cutoff is now somewhere between 3 and 4 hertz. How about a 330? And that is darn close to 45 degrees at 5 hertz. So the 330 ohm resistor and the 100 microfarad capacitor is possibly a very good mix, because 330 ohms is often what we use to limit the current in an LED, and I don't think we're going to be driving anything larger than that right now. But I want to point out a couple of things before we move away from this. We are designing a low-pass filter with a 5 hertz cutoff, which means at 5 hertz, 1 volt would become 0.7 volts. Or in the case of our rectifier circuit, what we expect is that 16 volts as a peak is going to become 11.1 volts. But will it? But will it really? Because the output waveform from our rectifier is not 5 hertz. The output from our rectifier is 120 hertz. And at 120 hertz, a 330 ohm resistor in series with a 100 microfarad capacitor is going to drop, ideally, 16 volts down to just 0.643 volts. So let's put these circuit components together and see what actually happens in the real world.